next video on exploring Verilog HDL. In this video, we are going to discuss levels of abstraction in Verilog HDL. The topics we are going to cover here is overview, switch level modeling, gate level modeling, data flow modeling, and behavioral modeling. First, let's dive into overview. Internals of each module can be defined at 4 levels of abstraction, depending on the needs of the design. The module behaves identical with the external environment irrespective of the level of abstraction at which module is described. Thus, the level of abstraction to describe a module can be changed without any change in the environment. The first highest level of abstraction is behavioral model. A module can be implemented in terms of design algorithm without concern for the hardware implementation. Designing at this level is very similar to C programming. The next level is data flow level. At this level, the module is designed by specifying the data flow. The designer is aware of how data flows between hardware and how the data is processed in the design. The next level is gate level. The module is implemented in terms of logic gates and interconnection between these gates. Design at this level is similar to describing a design in terms of gate level logic diagram. And the lowest level of abstraction is the switch level. A module can be implemented in terms of switches, storage nodes, and the interconnection between them. Now we are going to study detailed view of each modeling. First, we are going to deal with gate level modeling. Verilog supports basic logic gates as predefined primitives: AND, NAND, OR, NOR, XOR, XNOR, NOT, buffer. These are the primitives that are supported in Verilog. There is a code I have given, which is a Verilog code for an half adder. I have started with the keyboard module and given the module name as HA. A, B, S, C are the ports. A, B are A and B are my input port, and S and C are my output port. We know that sum is uh, the result of XORed inputs. So we are calling the primitive gate XOR, and we are giving the gate name as G1. The syntax to write this primitive gate is gate name in bracket. First you have to define output, then inputs. So XOR G1, S is my output, A and B are my input. And then carry is ANDed inputs. So AND G2 C comma A comma B. Then module is ended with N module. This is a simple code for an half adder using gate level modeling. So in real circuits, logic gates have delay associated with them. Gate delays allow the Verilog user to specify delays through the logic circuits. So the type of delay specifications. We have delay time, rise time, fall time. So these delay are specified in a particular fashion that I have specified there. And hashtag in bracket we are giving delay time and the gate name A1 output, then inputs. For rise and fall delay, we have and hashtag rise value comma fall value, then for gate name output and inputs. Example I have given, and hashtag of 5 A1 out comma I1 comma I2, which means we are giving a delay time of 5 nanoseconds. And the next example, or hash 4 comma 6 A2 out I1 comma I2, in which 4 is rise value and 6 is fall value. So moving on, The next modeling we are going to discuss is data flow modeling. Data flow modeling provides a powerful way to implement design. Verilog allows a circuit to be designed in terms of data flow between registers and how a design processes data rather than instantiation of individual gates. So the same code for an half adder I have given in data flow modeling. We are using assign keyword and some operators are there for data flow modeling, and I will share the operator model in my LinkedIn group. Module HAABSC. Input are A and B, output is S and C. Assign S is equal to A XOR B. That uh, symbol is XOR operation. Assign C is equal to A and B, and I have commented out one statement, assign hashtag 10 S is equal to A XOR B. That hashtag 10 is the delay. If you have any delay in the circuit, you can specify likewise. And we are ending our module with N module. This is a Verilog for an code for an half adder using data flow modeling. And some common questions that are coming in this data flow modeling are these. We will discuss each one by one. Difference between one OR and two OR operator. That symbol is representing OR. Then the second question is difference between double equal and triple equal operator. Then third is write a very low code for 2 cross 1, that is mux, not max, sorry, using conditional operator. Then fourth question is some values for A, B, C are given. We have to find the respective value for Y. So the first question answer is one single OR operator is bitwise OR and two OR is representing logical OR. Let's take an example. Here I have taken X is equal to 4 bit 1010 and Y is 4 bit 0000. So X OR Y is 4 bit 1010. X logical OR is means any one of the bit is high in X, that represents high, and if all the bits are low, then that represents 0. That is the logical OR. So it will equivalent to 1 or 0, which gives the result 1. Moving on, second question is difference between double equal and triple equal operator. In the both case, they are equality operator, but double equal does not include uh, the unknown values. For a particular variable, we have 4 values: 1, 0, don't care, and high impedance. Don't care is represented by X and high impedance is represented by Z. So if A equal to B, which is uh, equivalent to A equal to B, and the result is unknown if X or Z are in A or B. That is, they are not including X or Z in the input values. If we have to include that X and Z in the inputs, we have to use triple equal. That is case equality. A triple equal to B is A equal to B including X and Z. Moving on, the third question is write a Verilog code of 2 cross 1 mux using conditional operator. We are using module name as mux 2 cross 1 input. If we are representing wire, it will treat as wire. Otherwise, if we are not representing wire, default cases, it will treat it as a wire only. If you are representing it as a register, or if you want to represent output Y as register, then you have to represent output reg Y. Otherwise, it will treat it as a wire only. So if there is no wire represented, no issue. If you are representing wire, no issue. So module Mux 2 cross 1 is our module name. Input we have a comma b comma select line, then output is y. The conditional operator is given in the assign statement. Assign y is equal to select question mark b is to a semicolon, which means that if select line is high, then it will select b, otherwise it will select a. That is the conditional operator. Then moving on, the fourth question, we have uh, a is a register type and bc is 2-bit register type. We are giving a value 1 bit 1 and we have 2 bit 0 0, c 2 bit 1 0. So that curly bracket indicates concatenation, double curly bracket indicates concatenation. So in that result, we are making a into 4 bit, which means y is equal to 4b1111. In the second example, we are concatenating 4a and 2b, which means it will become 8 bit. First 4 bit will be from a and second 2 bits from 2 bit b. That is 8 bit 1111 00 then 00. In the last example, it will become 10 bit and the first 4 bit from a, then 2 bits from b and 1 2 bit from c. Moving on, next we are going to discuss behavioral modeling. We will discuss this behavioral modeling in our next video in a detailed manner, and also we will write some Verilog codes on the previous model also. Thank you.